Okay, this is section 2.2 on rates from Math Power 8. These are questions 4 through 15. Is it 15? Is that how far we went up to for question 15? 4 through 15. So the question number 4 says determine the unit rate in each situation. And remember, a unit rate, first of all, a rate in general, a rate expresses a comparison of two or more numbers, usually two, of two numbers in different units. Now, that's different than our definition for a ratio, which we did in section 2.1, because a ratio compares things like stars to moons, which are the same units, they're both shapes, or boys to girls in a classroom, which are the same units, which are students. But rates compare two numbers that are in different units. So for A, the numbers we're going to compare are 110 kilometers, which is distance, and we're going to compare that to 2 hours, which is time. And time and distance are units that are not related to each other whatsoever. So when we first attack this question, the first thing we have to ask ourselves is what is my first term in my rate going to be, and what is my second term going to be? So am I going to express the orca swimming in kilometers per hour, or am I going to express it in hours per kilometer, meaning how much time does it take the orca to go? This would be how much time does it take the orca to go 1 kilometer, or am I going to know how many kilometers it can go in 1 hour? Now the obvious answer is the one we use all the time is kilometers per hour, because that is a rate of speed that we're all familiar with, because every sign on every street and every highway has what we call a speed limit in kilometers per hour. So we're going to use the first one. That doesn't mean that this second rate of hours per kilometer is not something we might use someday, right? We might want to know if it was a distance of a kilometer, how long is it going to take the orca to go that distance? Then that we would use that. But we're going to put our 110 up here for in our kilometers area, and we're going to put our 2 hours down here. Now it says make a unit rate. Now this is a rate, and the difference between a rate and a unit rate is in a unit rate, the second term is 1. So we want to get it in kilometers per 1 hour. And to do that, way back in grade 5, you learned how to create equivalent fractions. And we're going to divide both by a common factor. So we know that this 55 kilometers per hour is the rate of speed, or the average rate of speed, because if it goes 110 kilometers in 2 hours, then it would go 55 kilometers in 1 hour, and therefore its rate of speed is 55 kilometers per hour. If we look at the other ones, if I change this now, the goose flies 800 kilometers in 12 and a half hours. Again, this is the exact same thing. We're looking for rate of speed, so we're going to have distance as our top number and time as our second. 800 kilometers over 12.5 hours. And if we're going to create a unit rate, we want our second term to be 1, which quite simply means we're going to divide both terms by 12.5. And 800 divided by 12.5, if I remember correctly, because we did this question yesterday, is 64, right? So therefore, the Canada Goose is flying at an average rate of speed of 64 kilometers per hour, which is quite fast. And C, I'll just leave that over there. I'll just do C over here. 45 daffodils in 30 minutes. So now we have a new unit. Do I want to know daffodils per minute, or how many minutes it takes to plant one daffodil? So we have to determine which one are we going to do, daffodils per minute or minutes per daffodil. Which one did you guys use? Did you guys all use daffodils per minute? How many daffodils per minute? Or did you use a different unit instead of minutes? Let's try it. Let's see what happens. So I'm going to choose the first one, daffodils per minute. And I'm going to put 45 daffodils in 30 minutes. And I'm going to divide both terms by 30. And 45 divided by 30 is 1.5. And 30 divided by 30 is 1. So it's 1.5 daffodils per minute. And I'm like, well, that's an okay unit rate. But if we chose a different unit rate, what would be a different one? Even though minutes was the time given, it probably would be better if we used what unit of time? Per hour, right? So if I said, well, you know what, I don't want this. I want to have per hour. Instead of over here, I could say, well, let's multiply 30 by 2. That's going to be 90 daffodils per 1 hour. So a unit rate is this person has a unit rate of 90 daffodils per hour. And that makes a little bit more sense because if you were comparing it, the decimals kind of muddle a little bit the efficiency of this particular person who plants daffodils for a living. And 90 daffodils per hour sounds pretty good, actually. She's a good daffodil planter. Question 5, again, we have the exact same question, except different things. So um, a blue whale eats 8 t of krill. Do you guys know what a krill is? A krill, yeah, it's like a little, tiny little sea organism. Looks like a shrimp, but it's tiny, tiny, almost microscopic. And 8 tons, just so you know, 1 ton, Tonne, a metric ton is 1,000 kilograms, or approximately 2,200 pounds, right? So that's like 16,000 pounds of krill in 2 days. That's a lot of poundage of krill, each whale. So unit rate, we're going to do krill over days. You could do days per krill. You can see how long does it take it to eat 1 ton of krill. You could do that. But we're going to use this one. So 8 tons in 2 days is going to be 4 tons in 1 day, or it eats 4 tons of krill per day. That's an easy one. You could probably do that in your head, no problem. And you might be able to do the second one in your head as well. The cruising speed of a blue whale. A lot of blue whale questions. Allows it to travel 193 kilometers in 10 hours. So we know from experience in our last one, we're going to use distance to time. You could do time to distance, but we're going to put 193 over 10 hours. And I can do this in my head because when I divide by 10, I simply move the decimal place in my number one place over. It's going to be 19.3. Therefore, the blue whale can travel at an average speed of approximately 19.3 kilometers per hour. Of course, it has to pause. I'm sure during those 10 hours, it would build up quite an appetite considering it needs to have 4 tons of krill a day. So it would probably pause to have a snack, which would, of course, decrease its overall speed. And who knows what it would be. I don't even know how often it eats. And then, of course, my favorite question, a bull moose bellows 15 times in 2.5 hours. And as we said before, a bull moose would bellow in order to let the ladies in the area know that it is available and is looking for love. So 15 times means it is desperate. So bellowing, we're going to have bellows to time, and we're going to put 15 bellows in 2.5 hours. Now, there are 2 ways we can go with this. We might want to know how many times it bellows per hour. We might want to know how many times it bellows per minute, or we might want to know how many times it bellows per day, right, on average. Now, the only problem with bellowing per day, what would be the problem with that? The assumption would be that the moose is not sleeping, right? It's just spending all of its time bellowing for no particular reason. So we're going to go per hour. We're going to divide both of these terms by 2.5. And we're going to see if we can do this in our head. How many 2.5s are there in 10? 4. How many 2.5s are there in 5? 2. How many 2.5s are there in 15? 6. So without grabbing a calculator automatically, I know that on average, a moose bellows 6 bellows per hour, right? That would be its average rate of bellowing. Question 6 talks about Gina. She works for $78 for working a 6-hour shift, and Assad makes $192 for working a 14-hour shift. You're looking, well, who makes more money? Well, you can't compare these two unless you have a unit rate of pay. So we want to know how much they make per hour. And once we know that, we'll know who has a greater hourly rate of pay. So we're going to put the common rate of dollars per hour. And for Gina, we're going to put $78 for 6 hours, which will be, how many 6s are there in 60? 10. How many 6s in 18? So how many 6s are there in 78? 13. So we're going to say her hourly rate of pay is $13 per hour. Where Assad makes 192.50 for 14 hours. Now, this one I'm not quite as well. Maybe we can. Now we're not going to do it in my head. Who am I kidding? We're going to go 192.5 divided by. That's not the wrong number. Divided by 14. So Assad makes 13.75 per hour. And therefore, now that we have it broken down into a unit rate, it becomes clear that Assad makes 75 cents more per hour. For question 7, we have 3 packages of mixed nuts. The first package has 300 grams. It costs $2.19. Then the next 2 are slightly bigger, but cost a little bit more. And we want to determine the unit price for 100 grams. And again, just like the last question with hourly rate of pay, if we know how much each 100 grams of these mixed nuts cost, we know which one is the better deal. So the question is, do I want to know grams per dollar or dollars per mass unit? And since this question says right here per 100 grams, that means that I want my grams to be my second term because I want to know how much it is for 100 grams. So I'm going to set it up 3 times. I'm going to put 1, and I'm going to put 219 for 300. For question 2, I'm going to put 309 for 500. And package nut 3, I'm going to put 483 for 700. Now the nice convenient thing about this is that it is really, really easy to create proportional unit rates of 100 grams. And we already talked about 100 grams is a hectogram, isn't it? We talked about our metric system. So it is technically a unit rate where the second term is 1 because 100 grams is 1 hectogram. And by doing so, I just have to divide all of them by 3 here. Divide each of them by 5. Divide each of them by 7. Let's see if we can do it in our head. $2.10 divided by 3 is 70 cents, and 9 divided by 3 is 3. So it's 73 cents per 100 grams. $3 divided by 5 is 60 cents, and 9 divided by 5 is 2.25. Oh boy, I'm not doing that in my head. So $3.09 divided by 5 is 61.8 cents. So we're actually going to keep the partial decimal. We're going to keep the fraction of a cent, 8/10 of a cent, right? It's actually this much money, 8/10 of a cent. Not quite a penny, but 8/10 of a cent. We're going to keep it. And then 483, $4.83 divided by 7 gives us a unit rate of 69 cents per 100 grams. So now that we have all 3 of those down, it's 73 cents for 100 grams. It's almost 62 cents for 100 grams, and it's 69 cents. So which one is the better deal? If you were trying to get the most mixed nuts for your dollar, you would want to buy the second nut package. It's the best deal. I'm going to make this a little smaller here because it's a little big. Bring it over here. Here we have milk that's in 3 sizes. Do we have to do this question? I'll let you skip it. That's right. We'll skip it. But we didn't skip this one, did we? All right. This was easier. There's only 2. Oh, shrink it. There we go. So it says Mala is shopping for honey. Her favorite brand is available in 2 sizes. Does anyone else here have a favorite brand of honey? Honey is disgusting. Well, that's so negative. Bees they work so hard for this. They want to make you happy, and you like the bees, but not the honey. Excellent. So what we need to do here is we need to determine which is the better buy. And in order to do that, we need to create unit rates in the same second term unit. So if I put the small and the large, and I'm going to put the typical dollar to volume, or 279 to 250 mils. And for the large, it's $9.59 for 1,000 mils. Now remember, as long as we're examining both jars in the same size container, we can compare them. So how many of you did this and made it into 100 mils? Did anyone do this? Nobody? Really? What's the better way to do it? Since this is already This is actually a unit rate, isn't it? Because 1,000 milliliters is one what? Liter. So this is already done for us. We don't have to do this. We can just leave it as is. It's happy. It's a unit rate. If I wanted to change this to a unit rate of 1,000 milliliters or 1 liter, I would simply multiply 250 by 4 because 250 times 4 is 1,000. At 279, well, I know right now before I even do the calculation which one's the better deal. Because what's $2.50 times 4? $10, right? So if this was 250 times 4, I know my answer is going to be $10 over here, which is more than it is already. So I know right off the bat that the large is the better deal. I'm just not sure by how much. So 279 multiplied by 4 is $11.16 per liter. So to make a liter of honey from the small, you'd need to spend $11.16. And to make a full liter of honey from this one, you only need to spend $9.59. So it's the better deal. I buy liters of honey and I have it all the time. One of my favorite snacks. Write this down because you're going to want to have it. Piece of bread, preferably fresh white, nice and soft. Peanut butter, Jif dark roasted peanut butter. Bananas, and a little drizzle of honey on top. And then, wait for it, a little high sprinkling of sea salt on top. Well, you try it and then tell me that. Do you like bananas? Do you like honey? Well, you're all crazy. Hang on, we're not even paused. We're still rambling on in the video. It says Trevor rode his mountain bike. Mr. Bridges rode his mountain bike 84 kilometers in 3 hours, and Jillian rode 70 kilometers in 2.5 hours. Who is the fastest cyclist? And how do you know? Well, we're going to know because we are going to actually create two unit rates. Trevor is 84 kilometers. We're going to distance to time. And we're going to Jillian is 70 kilometers in 2.5 hours. And we're going to make unit rates. This is going to be per 1 hour, and it's going to be per 1 hour. I'm going to do so by dividing top and bottom term in our rate by 2.5, and we're going to divide top and bottom term by 3. And if memory serves me correctly, this is going to work out to be equal. But let's do the math on this. How many 3s in 30? 10. How many 3s in 60? 20. How many left over to get to 24? There are 24. How many 3s in 24? 8. So my answer here is going to be 28. How many 2.5s are there in 10? 4. How many 2.5s are there in 70? 7 times 4, which is 28. So therefore, Trevor and Jillian have about, approximately, depending on how accurate the time and the speed is, the same cycling speed. They are the same fastness. Yes, that's a word. Shannon buys 12 granola bars for $9.96. That seems like a really weird price, but we'll roll with it. $9.96. Determine the price per bar. Give your answers in dollars and cents. So per bar, even though the money is my second number that's given, the per bar means bar is my second term. So the first thing I'm going to do is organize my brain. I want my money as my first term, and my bars as my second term. Because 12 bars, $9.96. If I'm going to get it per bar, I want to know how much it is for 1 bar. Let's see if we can do this in our head. How many 12? No, we can't do that. Can we? Is it possible? I don't think I could have got there. So therefore, it's 83 cents per 1 bar. Now, is your answer a ratio or a rate? It's a rate because they're different units. Bars and money are not the same units, unless, of course, you're talking about gold bars, then I guess that is a standard unit of currency somewhere. Now, this question is quite something. The rate at which glaciers melt is increasing globally. That is true, and this is 20 years old, this textbook. The Saskatchewan Glacier near Banff has receded 1.5 kilometers in 75 years, and the Peyto Glacier, shown below, receded 1,320 meters in those distance of time. So what has the greater annual rate of melting. So do we want to know the kilometers per year or years per kilometer? I think so. But I think actually even better than that, I think I want to change kilometers to meters. So I'm going to make a quick change here because I'm like, you know what, 1.5 seems like my answer is going to be a decimal if I use that. So I'm going to change it. So I'm going to put the Saskatchewan Glacier and the Peyto Glacier. So in meters, it's 1.5 kilometers, which is how many meters? 1,500 meters in a time frame of 75 years. Now the Peyto Glacier is a little bit more complicated. It actually gives us it in meters. So we're going to put 1,320 meters in, I have to do some thinking. Between 1923 and 1993 is 70 years. That's right. Now, if you didn't know that, you could have just used the old-fashioned subtraction. 1993 take away 1923 gives you 70 years. So now that we have that, we're like, oh, this is easy now. I can do this. This is no problem. Divide both by 75. How many fifth? There are two 75s, so there must be 20, right? 20 meters per year is the unit rate for that. How many 70s are there in? Yeah, I can't do that. So 1320 divided by 70 is 18.8. So look, I have to change it to the approximately equal to because we're rounding. So which one has the fastest rate of recession? The answer is the Saskatchewan Glacier is receding by 1.2 meters more per year. So if I actually ask that question, you could put the Saskatchewan is receding 1.2 meters more per year. If that makes sense, if you wanted to. Oh my heavens, we're already at 22 minutes into our video. Here we go. Question number 13. We got Joe and Sarah and Martin. And each of their cars went different distances and used different amounts of fuel. And we want to know which one is the best fuel has the best fuel consumption rate, or used the least amount of liters of gasoline to go a kilometer. So we have per kilometer written right here. And because we have per kilometer, we know kilometers this time is going to be our second term because we want to get it to per kilometer. So we're going to have liters per kilometer as our rate. For Joe, he was able to go 28 liters for 400 kilometers. Sarah was able to use 60 liters of gas to go 840. And Morton was able to use 20 liters to go 245 kilometers. So remember, the reason why I set this up properly is because right here, it said per kilometer, which means my second term had to be kilometers. And then I just put the appropriate numbers in. So I want to get how much gas per 1 kilometer. And usually if you look at cars, it actually doesn't use per kilometers. As we see this, if you go buy a car, which you will eventually, actually probably pretty soon in your lives, on the side window of the car, it always has the fuel efficiency. And it always expresses it for how much liters of gasoline it would take that car to, on average, travel 100 kilometers. So this 1 kilometer business that we're doing right now in A is not really a thing. So I'm going to divide both by 400 here. And I'm going to go, what's 28 divided by 400? And it's 0.07. So it takes 7 centiliters of gasoline to travel a kilometer. It's a thing. Divide 60 by 840. Oh, that's not 840. And that is, just a little bit more. So I'm going to keep a couple of significant. So 0.0714. I'm going to keep a few more there. And then I'm going to divide both by 245 here. And 20 divided by 245 is 0.0816, 0.0816. So which one uses the least amount of gas? Joe's car. Joe's car uses slightly less gas to go a kilometer. And it says, how could you change your answer in part A to express it as um, liters per 100 kilometers? Well, you could then do one of two things. You could then multiply both by 100 to get uh, 7 liters, 7 liters per 100 kilometers. Or what you could have done back here, you could have said, listen, if I want per 100 kilometers, which is what fuel efficiency ratios are, what do I divide 840 by to get 100? If you reverse it, what do I multiply 100 by to get 840? The answer is 8.4, right? So therefore, your multiplication or your division is the inverse operation. So I could have done this. I could have divided both by 8.4 to automatically go to that standard 100, oh, sorry, kilometers, not liters, 100 kilometers. And it would tell me that 60 divided by 8.4, it uses approximately 7.14 liters of gasoline to travel 100 kilometers. And here, I'm just going to do the same as my first one. It is approximately 8.16 liters to go 100 kilometers. Now, just for point of fact, it's approximately 55, 59, something like that. We'll say 50 kilometers, make it easy, to go to Charlottetown. So if you wanted to go to Charlottetown and back, so let's say you wanted to go to Charlottetown for whatever, shopping or something, you would probably travel just slightly over 100 kilometers, which means you would just use over 8.16 liters of gas if you were driving Martin's car. And since 1 liter of gas is approximately $1.25 right now, then if we take the 8.16 liters and multiply it by the cost of 1 liter of gas, even though this is not it would cost you approximately $10 to go to Charlottetown on gasoline, right? Which is fairly pricey. Mr. Bridges lives in Charlottetown, and so does Mr. Valet, and they commute every day from Charlottetown to Summerside to work. So, and Mr. Valet drives a truck, which I'm sure has a worse fuel efficiency ratio than this. We should ask him, if you ever have a chance, ask him what kind of fuel efficiency mileage do you get on your truck. And if it's more than this, then you know it costs him more than $10 a day to get into work. Question 14, it says conversion rates among currencies vary from day to day. The numbers of the table gives value of currencies. What is the value of $600 Canadian in euros? So what we're going to do here, this is kind of interesting because really what we're doing is we're setting up a ratio, right? We're not setting up a rate. We're setting up a comparison of Canadian dollars to European dollars, right? To euros. So we're setting up not a ratio, not a rate, but a ratio, really. It's comparing money to money. So if I say $600 Canadian, I don't know. Actually, I'm not going to do that yet. So since I'm setting up Canadian dollars to euros, 1 Canadian dollar is equivalent to 0.6940 euros. Right? That's the ratio of Canada dollars to European Union dollars, or EU. So $600 Canadian is equal to how much in euros? So what I'm going to do here is I'm really doing a proportion. I multiplied this by 600 to get 600. So I'm going to multiply this by 600. And when I take that decimal 6940, or just decimal 694, and multiply it by 600, it tells me that $600 Canadian would be 416.4 euros. And if I take that same value of 375, so again, the ratio of Canadian dollars to US dollars is 1 Canadian dollar is equal to 88 cents, 88.57 cents, which you can tell this textbook was written a long time ago because I think now it's 70 something for sure. $375 Canadian is equal to how much? So again, I'm going to multiply both sides by 375. And notice how important it was for this part here. I wanted to make sure my top number. So I just got tickled by my wife. So eight. Where are we at here? I've lost all. So if I take the rate of this U.S. dollar and multiply it by the 375, I get 332.13.75. So 332.1375, which is approximately $332.14 US. So if I took $375 into the bank and said I'd like to buy some US currency, and they gave you this rate of exchange, they would then give you $332.14 US for your 375 Canadian. And finally, the last one, one Canadian dollar is equal to a dollar. We get more Australian dollars, so we should travel to Australia is what this whole question is about. Equals this. So if I multiply the rate of exchange in Australia, so 1.1527 for every Canadian dollar multiplied by the 450 Canadian dollars I gave the bank, they're going to give me 518.72 approximately, because I rounded that. $518.72 Australian. This is the longest video I've ever made. As of right now, this is the longest of all time. Is this the last question? Okay. So the last question says Cindy Klassen from Winnipeg, Manitoba won 5 speed skating medals in the 2006 Olympics. As of March 2006, she held the world record in the 1,000, the 1,500, and 3,000 meter distances. Her times are shown here. Express each time in seconds. So what we have here is this 1:13.11. This is your minutes. This is your seconds. And this is your fractions of seconds, so 13.11 seconds. So it says express the time in seconds. Well, since this is equal to 60 seconds, and this time is equal to 73.11 seconds, right? Because that 1 minute is equal to 60 seconds. So it's 60 plus an additional 13, that's 73 seconds, and the 0.11 is still going to be a decimal. So 1 minute, 51 seconds, or 51.79, will be 110, because this is 60 again, 111. 111.79 seconds. And the third one, 3:53.34. This is going to be 180 seconds, because 3 minutes is 180 seconds. Plus 53 is 233.34 seconds. Okay. So those are the 3 times converted into just seconds, no minutes involved. I can erase those now. Keep those ones there. So those are our 3 times. And then it says, what was Cindy's speed in meters per second in the 1500? So here we have the 1500. Here we have her time. Per second. So because it says per second, we know that this number is going to go as the first or second term. If it's per second. Second term. So 111.79 is our second term. 1,500 meters is our top term. We want to have per second, which means our second term is going to be 1, which means I'm going to divide first and second term by 111.79. So 1,500 divided by that second term means that she was traveling, this is kind of fun, 13.4 meters every second. Now that's a huge distance. This wall right back here is 8 meters, right? So in 1 second, when she was on her average speed for her entire 1,500 thing, she would be traveling like 2 lengths of that wall basically every second. So she's motoring. And it says, how far does she skate in 10 seconds for the 3,000? So we're going to put the 3,000 here, and we're going to put our time for the 3,000 in seconds of 233.34. Oh, 3,000, thank you. So we're going to first take it down to 1 second, just like we did here. We're going to figure out how fast she was going on the 3,000, which is twice as much. Now we would expect that this speed would be the 3,000 average speed would be more or less than her 1,500. We would expect it to be slower, right? Because she's not going to go a greater distance at a higher rate of speed because her muscles just can't, lactic acid buildup and all that kind of stuff. So we're going to divide both by 233.34. And when we take the 3,000 divided by 233.34, her rate of speed here is approximately 12.9 per second. Well, we're only at 1 second now. So how do I get it back up to in 10 seconds? What am I going to do here? I'm just going to multiply by 10. And therefore, multiplying by 10 is so easy because when you multiply by 10, you just move the decimal. Her 10-second rate of speed on that 3,000 meter track is roughly 129 meters every 10 seconds. And 10 seconds would be a decasecond, if there's such a thing.